Hello, welcome to the PaintOmics tutorial. In this tutorial, we briefly introduce the concepts and different functionalities in PaintOmics and give a step-to-step guide about using PaintOmics to analyze your data. Now let's begin. Currently, multi-omics approaches have become popular for studying a wide range of biological systems, with multi-omics datasets now commonly obtained by both individual investigators and large organizations. Moreover, the number and diversity of measured omics modalities have also increased, with former studies combining at most 2 or 3 omics platforms. More recently, genomics, transcriptomics, methylomics, chromatin accessibility, proteomics, and metabolomics are often combined in a single study. We developed PaintOmics, a web server for the integrative analysis and visualization of any combination of omics modalities, using biological pathway maps. Basically, PaintOmics takes a list of omics datasets together with lists of significant features and paints this information on KEGG, reactome, or MapMan pathway maps. Pathway Enrichment Analysis, Pathway Interaction Network, Metabolite Hub Analysis, Metabolite Class Activity Analysis, Metagenes, and regulatory omics analysis methods are implemented in the application. PaintOmics 4 has several notable updates that improve and extend these analyses. 3 pathway databases are now supported: KEGG, reactome, and MapMan, providing more comprehensive pathway knowledge for animals and plants. New metabolite analysis methods fill gaps in traditional pathway-based enrichment methods. The regulatory omics module develops to analyze the contribution of regulatory layers such as microRNA, transcription factors, and RNA-binding proteins to regulate pathways. Now I will start to introduce the pathway enrichment analysis. Pathway analysis is a powerful tool for understanding the biology underlying the data contained in large lists of differentially expressed genes, metabolites, and proteins resulting from high-throughput profiling technologies. The central idea of this approach is to group these long lists of individual features into smaller sets, usually based on biological processes in which the molecules are known to be involved. One popular method for pathway analysis is pathway enrichment analysis, which is the approach adopted by the current version of PaintOmics 4. This algorithm aims to determine which biological pathways are regulated in the experiment for which multi-omics data were measured. First, the tool identifies the subset of genes, proteins, and metabolites from the input data that are annotated at each pathway belonging to any of the databases supported by PaintOmics. Then, PaintOmics uses a Fisher's exact test to evaluate if, for each pathway, the proportion of significant features that fall into the pathway is higher than the overall proportion of significant features in the dataset. This is called enrichment. A p-value is obtained that can be interpreted as the confidence that this overlap is not due to chance. The smaller the p-value, the more likely the presence of pathway features within the list of significant features is not due to random chance. As a general rule, a p-value of 0.05 is accepted as the threshold, indicating a statistically significant enrichment. Now let's look at the Metabolite Hub Analysis. One of the goals of multi-omics studies that combine metabolomics and gene expression or proteomics data is to associate changes in metabolite levels with the regulation of the enzymes that may contribute to metabolite turnover. PaintOmics 4 leverages pathway information to identify metabolites that have a high proportion of differentially expressed features in their close network. The hub analysis evaluates genes directly connected in the network of genes associated with the metabolite through up to 3 intermediate nodes. For the Metabolite Hub Analysis, PaintOmics 4 extracts the relationship between each metabolite and its neighbors across all pathways in the KEGG database for a given number of steps, typically 4, and generated a JSON file containing such information. 2 tests are implemented. The binomial test is used to evaluate for each differentially expressed metabolite the hypothesis that given the overall percentage of neighbors expressed genes P0 in the dataset, the proportion of differentially expressed genes linked to the metabolite is significantly higher than P0. P-values are corrected for multiple testing. Alternatively, the distribution in the overall metabolic network of the percentage of neighboring differentially expressed genes for metabolite nodes is computed, and the percentile position of each measured metabolite in this distribution is calculated. Metabolites with a high percentile value have a higher proportion of connecting differentially expressed genes than the majority of the metabolites in the database. The Metabolite Hub Analysis provides a graphical assessment of the magnitude of differential expression for linked genes and metabolites in a heat map. These visualization tools enable easy navigation across metabolite data, neighboring genes, and metabolic pathways. The next section is Metabolite Class Activity Analysis. Metabolomics experiments might be targeted to one or several metabolite classes for which an assumption of change exists. For example, in experiments evaluating growth, the hypothesis of central carbon metabolites changing their levels may lead to the measurement of this type of compound only. In this scenario, most of the measured entities might show a significant change, which impairs the application of traditional enrichment methods that rely on a non-change background. On the other hand, pathway enrichment for metabolomics data rarely results in significant results, as a few pathways compounds are frequently successfully measured. To test the hypothesis of a metabolite class being regulated, PaintOmics 4 implements a metabolite class activity analysis tool where a binomial test is used to assess the hypothesis of the proportion of significant compounds in a given measured metabolite class being higher than a user-defined threshold. If the user does not define an activity threshold, PaintOmics will use the average percentage of significant metabolites as the threshold for the generation automatically. P-values are corrected for multiple testing. These novel metabolomics analysis tools are provided as a separate tab in the main PaintOmics results panel. These visualization tools enable easy navigation between metabolite data, neighboring genes, and metabolic pathways. Metagenes are summary representations of the gene or protein omics values for a set of related pathways features that capture their common variation trend across multiple conditions or time points. PaintOmics computes metagenes at the node level and at the pathway level. Pathway node metagenes are calculated for those nodes with more than 4 annotated features, as this is often the case for protein complexes or mapman bins. Pathway metagenes are calculated considering all the genes or proteins annotated to the pathway. Note that metagenes are computed independently for each omics modality, and therefore might not always display the same trend. Principal components analysis is used for metagene calculation. Basically, the gene or protein omics values of multi-feature nodes or pathways are extracted and, after centering and scaling, PCA is applied, and a number of principal components are calculated that capture a significant proportion of the variability associated with the node or pathway. The metagenes are the PCA scores of these principal components, while the PCA loadings indicate the contribution of each feature to the principal components. Positive loading indicates a positive correlation between the omic value of the feature and the principal component, while negative loading indicates a negative correlation. When needed, metagene score values are adjusted to be positively correlated with the majority of the most contributing features to the principal component. PaintOmics 4 allows the user to view metagenes at pathway level in the pathway interaction network and view metagenes at node level directly in multi-omics pathway-based visualization. Let's look at the pathway interaction network. Although table diagrams are very helpful for understanding the pathway enrichment analysis results, they do not sufficiently represent the relationships that exist between the pathways. For example, the same gene or metabolite might be part of multiple pathways, creating a functional link between them. Alternatively, two pathways may show a similar trend of change when represented by metagene summaries, suggesting a regulatory relationship. PaintOmics uses a network-based approach to represent such biological interactions and creates interactive pathway networks where links represent either the existence of shared features or a correlation between their representing metagenes. Parameters for creating pathway networks can be adjusted by the user, and include the source of information representing network links and the threshold in the number of mapped features or the enrichment p-value for the pathway to be included in the network. The sizes of the nodes are directly proportional to the statistical significance of the represented pathway. Additionally, a clustering approach is applied to identify, based on metagene profiles, which pathways follow similar variation trends at each omic modality, and pathways can be colored by cluster, or by pathway category. Last but not least, users can modify the pathway clustering parameters to adjust their number, and can switch the rendering strategy for the network by choosing the omics type used to create the network. The figure shows an example of a network painted using two different approaches. Coloring by classification is shown in Figure A, and coloring by RNA sequencing trends is shown in Figure B. Finally, it is important to note that each node in the network is extended with a pop-up showing the pathway trend for the chosen omics type as shown in Figure A, as well as a supplementary panel summarizing the trends for each cluster as shown in Figure B, and an advanced view showing the trends for each omics type for a chosen pathway as shown in Figure C. The pathway network is a highly informative feature of PaintOmics 4. Researchers can easily switch between the different complexity and omics levels to explore the data, moving from the pathway network to the single pathway level and from there down to the level of individual genes with a single mouse click. The final section is regulatory omics analysis. PaintOmics 3 provided a regulatory omics option designed to upload data on features such as microRNA sequencing acting as regulators of gene expression. PaintOmics 4 extends this functionality to accept any type of transacting element operating on genes, transcripts, or proteins, and includes filtering functions to extract meaningful regulatory relationships. In addition to microRNA sequencing, transcription factors and splicing factors detected by RNA sequencing, RNA-binding proteins identified by clip sequencing can be analyzed with this option. The regulatory omics option takes a trans-regulatory feature data matrix with expression or activity values for regulators. In the conditions of the study, the regulator gene-protein mapping file is provided by the user. Together with an optional list of significant differentially expressed regulators, PaintOmics 4 filtering options include thresholds for positive or negative correlation to select the expected regulatory relationships. Applying these criteria, regulatory features, regulators, will be mapped to their targeted features and their corresponding pathways. A pathway enrichment score is calculated either based on the number of regulators mapping to each pathway or on the number of regulated genes present in the pathway. Enriched pathways for the regulatory omics modality represent biological processes that are significantly impacted by that regulatory layer.